Good morning, good afternoon, good evening, class. This is Mr. Osena, and today we're going to talk about derivatives. So the last part of this particular section. So to start off with, let's revisit tangent lines. So from earlier in this chapter, and I guess earlier in math, we had this equation. This equation describes the slope of a line. And as we know from previous studies in math, to find the slope of a line, all we really need is 2 points. We just need 1 point, x1, y1, and a second point, not y, second point, x2, y2. And with these 2 points, we can find the slope of any line. Okay? That's great. However, sometimes we're only given 1 point. However, even with only 1 point, we can always approximate the slope by picking an arbitrary point that is very close to the point that we're trying to investigate. And we came up with this particular equation. Okay, so f of x is basically, this is my y1, this is my x1, and then we just pick an arbitrary point. So a is arbitrary point that is close to x. That's close to x. So again, in the previous example, I used like if x is 1, then we pick a point that's very close to 1, like 1.0001. Okay. In effect, what we're really doing is we're calculating the limit of this function as x goes towards a. As x gets closer and closer to a, we're calculating the limit of this particular function. Okay. Now, usually in calculus, we write this function slightly differently, but it means exactly the same thing. Usually, we write it as follows. Okay. The previous equation is usually written like this, where we have the slope is equal to f of x plus h minus f of x, all divided by h. Okay, and what this basically means is, let's say I have a function. I'm going to do my best to draw a straight line. Okay, I have a function, and it goes like this. Okay, we'll pick a point x. So here's x, and then we're going to pick a second point somewhere over here. This point we'll call x plus h, where h is basically how far apart they are. Then we'll just pick consecutively closer and closer points until h is effectively 0. So we're going to calculate the slope as the limit as h goes to 0, because again h represents the distance between x and x plus h. And we want to get h getting closer and closer to our original point, or effectively we want h to be close to 0. So this is what we're going to say. The slope of the equation is the limit as h goes to 0 of f of x plus h, so that's the point near x, minus f of x, that's this point here, all divided by h, where h goes towards 0. Now I might ask yourselves, like, what's going on? Because if I take h to 0, this is going to become 0. Well, it's really no different than the previous equation that we wrote out here. If x goes to a, x minus a is also going to be 0. So we're just kind of eliminating that bit there. So this equation here, this is called, so this portion of the equation, this is called the derivative. Okay, this is the derivative. The derivative equation, which really basically means the following. The derivative is really the slope of the tangent line at point x on the graph. So that's really what the derivative is. Okay, the derivative is really just a slope. And usually we'll denote the derivative with this notation. We call it f prime of x. That's usually how we write the derivative. But all three of these mean the same. M, or slope, is really the derivative, and that's really the same thing as f prime. So all three of these, slope, so slope, derivative, derivative and f prime of x, and f prime of x are all the exact same thing. And you'll probably hear a lot of people, when they discuss derivative slope and f prime, they kind of interchange them. And I'll do that a lot as well. There you go. So this is the derivative equation. The derivative equation is this, and the derivative really means the slope of the tangent line at point x on this graph. All right, let's go through some examples of using this equation. So here's the first one. Calculate the derivative of f of x equals 4x plus 3. Now, before we get started, this is a linear equation. So this is linear equation in the form y equals mx plus b. So this is y equals mx plus b. Okay, and this shows us that this is slope. So this line, without even doing any calculation, has slope equal to 4. Okay, but let's calculate the derivative anyways, because now we have a check, because we know that the derivative of the slope of this line is 4. The derivative should equal 4 when we calculate it. So let us calculate the derivative. So the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So this is going to give me the following. We get 4x plus h plus 3 minus bracket 4x plus 3. Keep this in mind that you're subtracting the entire function, so you don't get confused by the signs, put the brackets in around f of x to remind yourself you're subtracting the whole function, not just part of it. Alright, let's expand this. So we'll get 4x plus 4h plus 3 minus 4x minus 3 all over h. A lot of things should cancel out, like the 4x here and the 4x there, a plus 3 and a minus 3. So we're really left with 4h divided by h. My h's drop out, and my limit equation reduces to the following. The limit as h goes to 0 of 4. This is just a constant. Since the limit of a constant will basically be the constant, its derivative is equal to 4. This is the exact same thing as the slope of our linear equation, so that's correct. So again here, slope equals derivative. So we're good to go. There we go. We're good. All right, let's try something slightly more complicated. So in this equation is no longer a linear equation. This equation is a quadratic, or I guess in some circles we can call it a parabolic equation, or a parabola. As we know, a parabola, let's draw a quick sketch of a parabola. Parabolas look like that. Okay? So they don't, compared to a line like this, a parabola doesn't really have a constant slope. So we would expect that the derivative, f prime of x, is going to equal a function of x. Function of x. Because again, the slope of this parabola always changes. The slope of a straight line does not. Right, so let's calculate this out. Right. Okay, so let's calculate this out. I'm just going to copy it into my sketchbook. Where's my sketchbook? There it is. Okay, it's already there. Okay, so I'm going to calculate the derivative of this. So we write my derivative equation. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So let's expand this a bit. So we'll get x plus h squared plus 3 times x plus h minus 10 minus, and again in brackets so I don't forget that we're subtracting the entire function and not just the first term. There we go. All over h. Okay. I'm kind of ignoring the limit here just to save myself a little bit of writing. Alright, let's expand the numerator some more. So we have x squared plus 2xh plus h squared plus 3x plus 3h minus 10 minus x squared minus 3x minus 10. And this is going to be all over h. Okay. A bunch of things should cancel out. For example, this x squared will cancel out that x squared. This plus 3x will cancel out this plus 3x. Oh, and I made a mistake. This should be a plus 10, so it'll cancel out this minus 10. Again, the reason this is a plus 10 is because it's negative times negative. It should be a negative 10. Alright, so then we're left with 2xh plus h squared plus 3h all divided by h. A bunch of h's will cancel out. That drops in power, that's there, so we're really left with the following. 2x plus 3 plus h. And I should say again, we're calculating the limit as h goes to 0. When we calculate that limit, h goes to 0, this drops out, so the limit is approximately 2x plus 3. Okay? So that is how the line, that is the derivative. So this is f prime of x. So this is the derivative. I should write down. So this derivative of f of x. Or basically this is the equation of the slope of the tangent line of that parabola. So if my parabola is here, my tangent lines, so 1 tangent line, 2 tangent line, 3, whatever. Those tangent lines, all the slopes can be approximated or calculated, not approximated, calculated using this function. Because this function is the derivative of f of x, or the slope of f of x at the point x. Alright, so that's how we calculate that derivative. Okay. Alright, another example. Here we have a graph of f of x, and where is the function's derivative the greatest, and where is the function's derivative the least? Now remember what derivative means. Derivative means slope. So derivative is slope. Okay, so looking on this graph, where is the slope the greatest? Well, we're going to look for a place where the tangent line is really steep. And that would probably occur somewhere in this region, because this region appears to be the steepest region. Okay, it's obviously not here, because here my tangent line is going to be fairly straight, or a horizontal line, and gets steeper and steeper and steeper. And eventually around this region we have a tangent line that is really steep, like that. So it's probably going to be somewhere there. Maybe x equals 0 is probably where it's going to be. Now where's the tangent line the smallest? Well, the smallest slope, where's the slope of the tangent line the smallest? Smallest slope we can get is 0. We have a couple of regions of 0 slope. We have a 0 slope here. We have a 0 slope here. And we have a 0 slope right at the tip of that arch and right at the tip of this arch. Okay, so the greatest will occur probably here, and the least will occur here, right at the tip there, right at the tip there, and there. Because again, derivative is really just slope, so if we're looking for a large derivative, we just look for a spot on the graph where there's a steep tangent line. The least will be if we look on the part of the graph where there is a very shallow tangent line. And those will be the spots where the function's derivative is the greatest and the least. Alright. If you have any questions, you can feel free to come see me in class. The assignment for today is as follows. Good luck.